Wade, and this is Lab 3, the magnetic field of a bar magnet. So to get started, the purpose of this experiment was to make a computational model representing a magnetic field and to observe the relationship between magnetic fields and the observable distance. It was also to determine a magnetic dipole and to develop a better understanding of the Biot-Savart law and other formulas of magnetic fields. So the models and fundamental physics principles used in this experiment are on the screen now. The first and second experiment help describe the magnitude of the magnetic dipole and calculate the magnetic dipole moment. In the third experiment, n is assumed to be -3. And the fourth experiment, it shows the formula for the magnetic field due to a dipole at any location, which is known as the Biot-Savart law. The results of this experiment were found to be that the magnetic dipole moment was 1.01 am squared. The magnetic field proportional to the distance was -3.5. The experimental B-net was 4.775, and the computational B-net was 3.46. So the experiment itself is done by first downloading a magnetometer app on your smartphone. Then you adjust the phone until Bx is 0, and that means that the phone is facing north. Then you place a meter stick perpendicular to the width of the phone, and then you find the sensor of the magnetometer on the phone. This is done by first sliding the phone perpendicular to the phone, or sliding the phone perpendicular until the X component is at its max, and then you place a piece of tape at that width. Then you rotate the phone 90 degrees and slide the phone until the Y component is at its max, and you place a piece of tape there as well. And then the location of the sensor is at the intersection of the tapes. Now, the first part of this experiment is done by finding the distance between the sensor and the magnet, where Bx is 20 nanoteslas, and that's done twice. And then you're going to do that same step, but for the value of 70 nanoteslas, 120 nanoteslas, 170, and 220. The data for the experiment are on the screen now. And after taking the natural log of both sides, the slope was found to be -3.5, which is a bit above, or below, I guess, the predicted -3 value. Here are my calculations done by hand. And then the next procedure is to find dperp, or the distance perpendicular, where the magnetic field is 100 nanoteslas. You then record the Y component at this location, and then you align a second ruler perpendicular to the first and in line with the sensor, and move your phone along that line until D is equal to dperp. Then you record the X, Y, and Z values and find the BY. Then you repeat these steps twice and record the data. The data I found is shown on the screen here. I found the experimental B-net to be 3.123 e to the -5, 2.727 e to the -5, and this created a B-net of 4.775. So some observations that I had when I was doing the experiment were that the X component increased as the magnetic field increased. It also showed that B Earth only needs to be subtracted from the Y component. And when the magnetometer is far away from the x-axis, the magnetic field in the x direction is almost 0. Now, in this experiment, there were some assumptions. The first being that there was no external magnetic field acting on the system other than the magnet, and that the initial Bx of the lab was 0. Excuse me. All right, now moving on to the code. So the code I have spread over 2 different slides. I created 2 magnetic fields on the axis arrows and 4 off of it. And then I calculated the magnetic field from an observation location of 45 degrees. And as you can see, here is the code at work. And it found that the B at a 45 degree angle was found to be 1.01 e to the -5, 3.29 e to the -5, 0, and this created a total magnitude of 3.469, which is notably below the experimental value. So there were likely some sources of error, especially given the discrepancy between the computational and the experimental model. And that's likely due to measurement errors, although it could also be due to the external magnetic fields. And in this experiment, there are some big what-if questions, which are on the screen here. First one is, what if you had oriented the experiment to compensate for magnetic north? And in that case, the exposition would either be greater or less than the theoretical, and it would be skewed north because this calculated the magnetic dipole and would be affected. The second question is, what if you were to stick two identical magnets together? And that would result in the direction of the magnetic fields being the same, but it would be double the magnitude, and the magnitude of the magnetic field would be greater if there were two magnets. All right, thank you.